Hi everyone, welcome to this second video on Introduction to Deep Learning Theory. At this second video, we're going to take a look at classification basics and the perceptron definition. Much of the content of this video is based on the free course from Udacity with title Intro to Deep Learning with PyTorch by Facebook Artificial Intelligence, the link of which you can find here. So, what a neural network is? Well, a neural network really looks like this. In fact, this is a very small neural network, even though it looks a little bit scary. Now, what a neural network is? Well, in fact, it is a universal function approximator. And what I mean by that? Well, it turns that a neural network excels at approximating the best possible function that can do one of the two things that we will see. First, it could be a function that can separate sets of given points. By separating sets of points or sets of data, this is what we call classification, and that allows you to detect which categories some of the inputs belong to. So this is an example where you feed a cat picture to the neural network classifier and it returns a label that what I saw is a cat. So by being able to separate, to categorize sets of data, this is what we mean when we deal with classification problems. The other thing would be intersecting sets of given points. That is, try to make our neural network go through those points as much as possible. And this is what we call regression. And regression, in fact, produces continuous sets of values following a supervised training. And to visualize this could be something like passing the past days of stock exchange. And by passing this data, the neural network would be able to predict tomorrow's stock price. So this is what regression does. Now, a neural network is calibrating its weights, which is actually the training part, in order to achieve this amazing power by something we call deep learning. Now, what I mean by saying calibrating weights? Well, in fact, when we are about to start training neural networks, we have already defined the architecture. So we have random weights for all our neurons. And with deep learning, we will first define those architectures and then we will alter the values of those weights to come up with a better approximation. And the more we train and the better approximation we get, this is the training part. So let's visualize all this, right? So let's see what deep learning is when we say that deep learning, in fact, is the science of defining and training deep neural networks. Now, I've done this in Photoshop. I hope you like it. One idea could be like being at the beach and we have blue and red marbles at the sand. And we ask a kid, can you draw a line that separates the blue from the red marbles? That's what the neural network does, the same as the kid draws a line that separates the blue from the red marbles. Now, let's clean this up a little bit and move it to the left. All right, so this is still our beach example. Now, let's take a look into something a little bit more complex, like this one. Well, we cannot really get away with a simple line here, as you see. So in many cases, we might need to come up with something more complex in order to separate our points. So as I said, this is what the classification is, separating our data and thus classifying it, categorizing our data. The other thing that we talked about was regression, where we try to intersect our data. We try to go through our points and find the line that goes best through those points. So something like that. And this is regression. So these are two different function approximations. The first tries to find the best line that separates our data based on their labels, and the second tries to go through those data. All right? But in this video, as we said, we will focus on classification. So forget regression for a moment and focus on classification alone. Now, let's get into Udacity's notes. Anything that I make use from Udacity's notes will have this annotation here, all right? So whenever you see source Udacity, it means that this note came from Udacity. So let's continue and say that we have the example of acceptance at the university. And in order to accept students at the university, let's say that we take two things into account. The test grades, the tests and the grades, okay? So these are the two things that we will take into account into accepting or rejecting student. So let's say that we have the first student who did really well. I mean, he got a 9 out of 10 at the test and had an overall 8 out of 10 at the grades. And this student did get accepted. Now we had another student, student 2, who did terribly at the test. He got 3 out of 10 at the test and scored only 4 out of 10 at the grades. And this student got rejected. Now, this is labeled data because other than given the test and the grade scores, we are also given the answer that who got accepted and who got rejected. And that's what we do with supervised learning. We provide label to the data, and then when we are given data without label, we try to predict what that label would be. So for a third student, the student 3, who got 7 out of 10 at the test and only 6 out of 10 at the grades. He's somewhere in between the first and the second student. And the question is, will this student get accepted or rejected? Well, let's put all this to a graph. So we will make a two-dimensional graph here. We have on x-axis the test and on y-axis the grades. Now, we will plot at 3.4 location the student who got rejected, and at 9.8 location, the student who got accepted. Now, the student with test 7 and grade 6, which appears to be at that point, did he get accepted or rejected? That's the question. And to answer this question, we have to put more data. So now by looking at the previous data, we can better pinpoint with our eye if this student will get accepted or rejected. And as you can see, since he will end up in this location, it appears that he is at the blue area, right? But don't just answer now. Let's look at it in a neural network perspective. We said that the neural network defines a function that separates sets. So here we might get away with a linear function that separates with a line our data. And this line is this one. So this line will be our model from now on, and this is the one that we will use as a neural network. Well, our model is not perfect. As you will see, it makes certain mistakes, as there are some red points in the blue area and some blue points in the red area. But since this model separates most our dataset correctly, we can get away with it and say that this will be our model. Now, the question is that yes, since the student is on the right side of the line, he does get accepted. All right? And let's look at this in a more mathematical perspective. The question though remains how we find this line, okay? And before we answer this is, as I said, in a more mathematical perspective, look what this line really is before we look at how to find it. Now, in order to look at it mathematically, we have to draw about the x and the y axis. We have to look at what happens in the x and the y axis. However, because we are dealing with neural network here, the x-axis is the test and the y-axis is the grades. But for us, these are two separate inputs. So it could be our x1 input and our x2 input. So since these are inputs, we won't refer to this as x and y, but as x1 and x2. So here I drew x1 and I will annotate here x2. So now we have y x1 and x2 representing our inputs. And that could be, the boundary line will be 2x1 plus x2 minus 18. And that is a linear function, a linear equation. All right. And what does this really mean? It means that we will take into account 2 times the test plus 1 time the grades minus 18. All right, so we had this student who scored 6 at the test and 7 at the grades. Sorry, 7 at the test and 6 at the grades. And he was plotted here, right? Now let's look into this. Okay, what does this mean? It means that the prediction will say that if x, y, okay, or x1, x2, for that equation gives us a result greater than or equal to 0, we assume that this person gets accepted. Otherwise, we assume that this person gets rejected. Now, if we say 7, which is the score of the test, so 2 times test, 7 times 2 is 14, plus 1 times 6 is 6, that makes us have 20 minus 18 equals plus 2. So all indeed, plus 2 is greater than 0, so that person gets accepted. So our model defines that this point is at the blue area. Okay, so that's our linear equation here. The thing is, of course, how we find this linear equation. That's the job of the neural network, right? Now, in order to make this more formal, we could say that we have two inputs, x1, x2, with two multipliers, okay? The multiplier of x1, which was 2 as we remember, and the multiplier of x2, which was 1, plus the bias, which is a constant that we made it be minus 18. So we can say that the boundary line is w1x1 plus w2x2 plus b equals 0, which we can short write as wx plus b equal 0. Now, we can say that we have the vector of the weights, that is the vector of the multipliers, and the vector of the inputs. So we have that so far. The other thing that we were missing was the label. Well, actually, you see, there is a label y that we are given for every point, as we know that, for example, the person who scored 9 at the test and 5 at the grades was labeled blue. He was given the label 1. So by giving the label 1, we used this point as part of our training. And since we got all those points labeled either 1 or 0 for blue and red, we were able to define a line based on all those points. So now that so this is one vital part of supervised learning, because we are already given the values of the data. Now that we have the values of the data based on which we were able to draw this line, we can now make predictions, okay? So our prediction, instead of being y, it will be y hat. This is our prediction, where we are given a gray point, in fact, and based on our model, we decide which side of the fence it goes. So if we find a point here, it will mean that based on our linear equation, the result will be positive, so we will call it blue. Or if it's here, it will be negative, so we will call it red. So our y hat is again 1 if the result coming out of this equation puts us on this side of the fence, or 0 if it puts us on this side of the fence. So that's the prediction, and that's our y hat. And as we see, our predictions are not perfect, as we saw that our model separates the points like that here. So there could be a few mistakes for the predictions that we might do in the future. And equivalently, there are some blue points in the red area for the rejections. While in fact, the data set of positive was this one that contains the error here, and of the negatives was this one that we can see here, the zeros, maybe not the negatives. So what we have really seen so far is this thing here. I mean, let's take the equivalent of a music console slider. So we have a music console and we have the sliders that amplify certain frequencies, that allow some frequencies to be heard more than others. And when we say that put more bass or remove a little bit of tremble, we move the sliders of the music console up and down, and we allow frequencies to be heard more than others. Equivalently, in our neural network, we allow some inputs to be heard more than the others. Like in the example of the test, we allowed the test to be heard twice as much compared to the grades. All right, and this is what we did. 1 second to remove this pointer. All right, and now when we have trained our network completely and it's okay, we stop moving the sliders and we leave them like that. We know now that we have a line that is correct, in a correct position, okay? And that's the best approximation that we get. So once we have the best approximation, we stop moving our line. And if I go back again here, the line, the ghost that is moving those sliders during the training is our neural network trainer, all right? So as I said, when the trainer is done, it's finished, we leave the weights intact the way they are, as we have now the best possible approximation. So let's visualize this further with a live example. So here, you can follow this example by looking at this link here at the top. This is exactly the test. You see here it says test, the test grades example, all right? The test grades example. All right. Now, for this, we have the linear equation of, we have weights for our first axis, our x-axis here, and the weights for our y-axis, which is our x2, and then we have the bias, which is the constant 1 multiplied by minus 18. So we can say that we have here again a third weight when it comes to the bias. And now let's visualize how the bias works and how the weights work. Now, by moving the slider of our music console, okay, here for the second weight, we see that we change the angle of the equation, right? So now this is the 2W1, 3.1W, sorry, this is the 2x1, 3.1x2 minus 18, would define this kind of equation, right? This kind of line. So by moving our second weight, we see that we move across the test axis, right? If we move this slider, we see that we move across the grades axis. Okay, so, and by moving the bias, we see that we make a parallel movement to our angle. So if I have, for example, this kind of line that is almost horizontal, altering the bias will move the line up and down. While if I have, let's say, a vertical line like this one, moving the bias, altering the bias will move the line right and left. And if I have a diagonal line, moving the bias altering the bias will move the line uh, diagonally. So the bias changes the position of the line while the rest of our weights change the angle of the line. And this is when it comes to a two-dimensional linear equation, okay? So I hope you understood how the weights visualized as music console sliders affect the result of the line. Now, a neural network, what it really has to do is find the best possible way to alter those three parameters in order to get the line that will separate the blue from the red points. So it would need to go to minus, let's say, 18, as we said. It would have to go to 2 here and 1 here, and this is, as you can see here, this is 2 times x1, so it is 2 times the test times 1 times the grades minus 18. And so this is what our neural network has to do in order to define the best line that would separate our points. So I hope now you have understood how the weights and the bias come to play when it comes to neural networks. Now, so far we have seen two inputs, the test and the grade. And I mean, you can see it here. Here is a test here on the right and the grades up here, right? Now, what comes if we have some more? Right, so we have seen so far grades and tests, but let's say that we had one more condition based on which we want to uh, identify whether we will allow students to be accepted or rejected. And so far you have seen that we have used two dimensions, one dimension for one input, one dimension for the other input, and that is the x dimension for the test and the y dimension for the grades. Let me go back one sec here. So you see that we have the grades on one dimension and the test on the other. Now, what would happen if we had a third dimension like the class rank? Now, as you understand, yes, this would be a third dimension. We would need a z-axis, all right, in order to plot this. And now we would have three axes for the grades, for the class, and for the test. And our data would, in fact, fly in 3D, all right? And now we have a three axis, but we would have a two-dimensional boundary that would go through them, which would be our prediction, all right? So the boundary plane would be 1 minus the dimension of our data. As we have a line in the two dimension, we have a two-dimensional plane in the three dimensions. So the only thing, in fact, however, that changed was that in our inputs, let me bring back the laser pointer. Okay, here. In our inputs, we had W1x1, W2x2, and now we will simply have W3x3 plus bias. So we just added one more input. So even though the dimensionality changed, in fact, we simply introduced one more input, nothing more. And we can still write it as Wx plus b equal 0, where still the prediction would be the same, that is If the result of our equation is greater than or equal to 0, we assume that the student got accepted, otherwise he got rejected. Now, what happens if we have even more? I mean, we can visualize up to 3 dimensions, but from 4 dimensions and on, it's hard to visualize. But no matter what, we simply add more input. So it might be hard to show it visually here, but you get the big picture. So if we have n conditions from x1 to xn plus a label, we could say, for example, that our acceptance conditions will depend on how he did on the first exam, on the second exam, on the grades, on the essay, on any other thing. And based on this, we definitely have to also have a pass or fail. So we give the whatever happened to the first student, and if he passed or if he didn't pass, so that we pass those labels as well to our trainer so that we can get our predictions later. So that's all that has to do with more dimensions. So more inputs mean more dimensions, but this doesn't mean more complexity necessarily, okay? Now, as I said, the boundary will be n minus 1 on the dimension. So if we have n dimensions, the boundary will be those dimensions minus 1, as it was in the case of the two-dimensional hyperplane on the three-dimension equivalent that we saw here, right? So now this will still be written as wx1 plus w2x2 plus w3x3 plus w4x4 all the way to wn xn. So that's the only change. And again, this can be still short written as wx plus b equals 0, and of course the prediction will remain the same. So nothing changed here, just more conditions to take into account. Now let's have a small math quiz because in order to multiply the weights with the inputs, we will have to do matrix multiplication. Don't worry, you won't do this. TensorFlow or PyTorch will do this for you, but you have to know what we're doing, right? Now, so let's look at this example. We still have n inputs for one value. Okay, so we have n inputs which end up to one neuron, and the result will be 1 or 0. All right, so what would be the best dimensions, sorry, what would be the dimensions for the input features x, the weights w, and the bias b to satisfy wx plus b? And those are the possible answers. Now we'll come up with the answer to this. So we will come up with a solution. I want you to freeze the video for one moment and think about it, and then watch the solution. So moving on to the solution. Now, when we multiply matrices, so let's say we have a matrix m by n multiplied with another matrix n by k. In order to multiply matrices, we have the rows and columns, right? And rows and columns. The columns of the amount of columns of the first matrix must match the amount of rows of the second matrix. So this must match. So since the amount of uh, columns of the first must match the amount of rows of the second, it means directly that the first, we can do this here, right? It's 1 and 1, so we can continue with this. The second answer is definitely wrong because we cannot multiply 1 by n with another matrix 1 by n. It should be the other way around, right? So from this, we know definitely that the second possible answer is totally wrong. We cannot go on with this. So we keep the first, the third, and the fourth, right? Now, let's continue. When we multiply a matrix, okay, we can multiply it if we have this condition, or the resulting matrix will be m by k. All right. So the rows of the first with the columns of the second will form the resulting matrix of this multiplication. But we said here that we have n inputs ending up to a single neuron. So we will have one result, a pass, a yes, or a no. So we will have a number, a scalar, right? So we will have a one by one matrix. This is a scalar. Since it's a result of yes, no. So we have to have one by one resulting matrix. And let's look at this. Okay, here we can do multiplication, but in the first example, we'll have n by n matrix result, which is not what we want. So the first answer is also wrong. So we are left with the third and the fourth answer, as they both allow us to multiply and they will produce a one by one result. However, when it comes to the bias, we see that the bias would give, in the fourth case, when it comes to the bias, it will end up with a 1 by n result. So we want to still finish up with a 1 by 1 result. So the correct answer is the third one. So in this math fast quiz about matrix multiplication, this is the correct answer. Now, let's look into perceptrons a little bit, right? So let's visualize what we have already seen, all right? So we stick on the same line, 2 times test plus 1 times grades minus 18. So we can visualize this like that, okay? So we have two inputs, one coming in with a 7 and the other coming in with a 6. We already know from our past data what we have here as a function. We plot this to the right side of the fence that is defined by our line. So we say that yes, the student gets accepted, right? So this is what a perceptron does. But let's look at the anatomy a little bit better. Now, we have the 7 with which is multiplied by 2, as we said, and we have the grades of 6, which is multiplied by 1, and the summation of these two, we remove 18, and we have a pass or fail. Okay, now let's look at this into a little bit further. Now, what this will do, we can also have the bias as a constant 1 always, multiplied by a weight minus 18, for example. So this could be a third input in our case, correct? Now, what we have is 2 times 7 coming here based uh, on our weight here, which was 2. 1 times 6 minus 18 times 1 equals 2. And we say 18 minus 1 because it was 1 the input and minus 18 the weight in case we move the bias outside together with the other inputs. Now all this gives us a result of 2. When the 2 is yes, greater than or equal to 0, yes, so we are still looking at the same thing in different ways, right? Now, when it comes to n inputs, this could be from x1 to xn with w1 all the way up to wn for the inputs, and the summation result of all these weights multiplied by their inputs plus bias from 1 to n, from the first to the nth, would determine whether the student has passed or failed, which is again the equivalent of wx plus b greater than or equal to 0, right? So far, we have been looking at the step function. And here, by the way, I have a typo. This should be 0 here instead of 1, so pardon me. So what the step function says is the following. For any value that is negative, you return 0. And from 0 and on, from 0 to positive, you will just return 1. Okay? So this is what we said before. Anything that is below 0, return 0, which is the value of y here. And for any values of x that is greater than 0, you will return 1. So we on the x, we return either this or that, depending on our x. Correct? Now, we can take this outside our function, our linear function, because it's a decision-making process. I mean, we could say if the value is greater than or equal to 2, or if it is greater than or equal to 1.5, or whatever. So as this is a decision-making part, we can separate it from the summation that we have here in our linear function, because we might use some different strategy later, right? So this step function is in fact what we see here. So we have our linear function, which is a summation. We have our decision maker, which is our step function in this case, and our result based on that function. And this step function is what we call one type of activation functions. We could replace this step function to a different activation function later in the future. But for now, we will always know that we will have an activation function, in our case, the step function, okay, which this step function will decide based on the summation whether our neuron fires or doesn't fire. And finally, I need to say that the very same thing can be represented with the bias as an input here, or if we take it inside the summation here. All right, so we will see different representations representing the same thing with the bias outside as an input or inside. Okay, so there are both representations represent the same thing. Now, what is a perceptron? Well, the perceptron is well, actually something like the dendrites of the brain. Well, you see in the dendrites, they receive some input, they make a kind of calculation, let's say, inside and fire to the next neuron. All right. We equivalently we have some inputs here. We make a summation. We have the decision-making part, which is our activation function, that based on the summation decides if it will fire or not as an output or as an input to another neuron. And as we see from the analogy with the biological neurons, a neuron can connect to other neurons. The input that we see here can be the output of other neurons. So that's what makes a neural network. And this is what we see here in a biological model where a neuron is connected with more neurons and we have a network of neurons. All right, so that's what we will also do with the artificial neural networks compared to the biological neural networks. I hope this first video about classification and perceptrons was helpful to you. There are many more to come. Leave your comments below and I will be happy to answer any possible questions. Have a nice day.